All right, well, thanks for coming. I'll be talking about GooFit. GooFit is a library that was designed to resemble the very popular GooFit library, but it was targeted at doing computations on GPUs. It's really focused on performance, providing a higher performance than GooFit was able to provide at the time. Later, support for OpenMP was added, and this library handles a variety of different situations, including it has a variety of PDFs. It can handle PDF composition. It can do bin and unbin fits, and it's really targeted toward amplitude analyses. So it's meant to be general purpose as well. So there really are three categories of GooFit users. The first category would be using the composition features. That's this is sort of illustrated here on the left, where you take variables, you find a variety of variables, you put them together in PDFs, you can combine PDFs using combination PDFs, multiplication, addition, etc., a variety of different combination PDFs that are provided, and then run this into your fitter, and then the fitter updates your variables. And there's just the second category of users would be ones who can actually write PDFs themselves. You can extend this with your own PDFs. The highest category of users would be ones who would actually help extend or work on the core itself. So I mentioned GPUs. Let me just spend just a second showing why we're interested in using GPUs. On the top here, I have an example of a computer. It happens to be my laptop, MacBook, and it's got 2 cores, around 3 megahertz, and it can, at best, do about 16 flops per cycle. That's if you're using all the vectorization features it provides. And that ends up with about 100 megaflops. On a server, you might have, you can see below it, you might have roughly a gigaflop of performance. That's you'll see this computer show up in a later slide. Whereas if you take a look at the graphics cards, they tend to be measured in teraflops, not mega or gigaflops. And this comes with a few caveats. It has a different programming language. You have to do the same calculation on a large number of values at the same time. And it has its own separate memory model, so you have to deal with memory transfer and things like that. But still, these are very, very exciting numbers. They promise a very impressive level of performance for a decent cost. You'll see examples of 3 of these. We don't have a example of a 1080. This is sort of the top level gamer board. Of course, if you want to vote for Vista's hybrid poster, make sure you get it in the second place. Then we'll have it 1080. Place down there. So we already have a P100. So I know where it came from. So here's some examples of the speed. This is the Pi 0. This is the original GooFit code running on a fairly old computer. I don't have access to that original computer anymore. It took about 5 hours to complete. By simply rewriting this in GooFit, running on a dual-core system, also not particularly recent, though this actually is a computer I have. You can reduce that to about 20 minutes. Using a GPU, you can take it down, P100, you can take it down to 20 seconds. Even with a gamer board like this one, you can get it down into the minute or 2 range. That's a very, it's a very cheap card. So it really changes the problems that you're looking at. It reduces the time to insight. It lets you do things you weren't continuing to do before. If you can take something that takes 5 hours and down to a minute, maybe you'll run 1,000 bits before you go and run a few. We also tried this on a different data set I just pointed out because you'll see it in the next slide. And this is showing that it scales very, very well as you go up to a larger number of cores of OpenMP. So let me briefly go into the history of GooFit. GooFit's first official release was in 2013, version 0.1. Went under quite a bit of development for the next year, and then disappeared. Well, no, what actually was happening is it forked. It was still very active. You just didn't see much in the master branch. You had a variety of different forks. Analyses were happening. Code is being written, but not much is happening in the master branch. And here, at the end of 2016, what I call the modernization process occurred. Several of these branches were merged, and a variety of new features were added, and I'll be talking about that now. The thing that I find quite exciting, and that you will too if you've ever tried to build GooFit, is that it now builds using CMake. The it supports different IDEs like Xcode. It supports Max now too. It supports the single-threaded backend, which is necessary for normal people to build it on a Mac. You can use OpenMP on a Mac, but you have to be slightly crazy. It also automatically downloads data files, including several new data sets that were released, including the ZACFit data that you saw on the previous page. So you can now run both of those examples yourself, and they will download for you when you build GooFit. It covers your libraries automatically, partially because it's CMake. Some of the library discovery tools, like the Find Root, are state-of-the-art, and if you want to use them yourselves, they're in the separate Git repository, and you can grab that for your own project, even if you don't want to use GooFit. There are a variety of other build features, most important of which are the continuous integration builds, the beginning of unit tests, and actually updated documentation. Really easy to get started. If you happen to not believe me that these 4 lines are enough, this is actually a brand new pristine Docker container for Ubuntu. So this is starting from nothing in Ubuntu. This is what it takes to get going. There are examples just like this out there for a variety of other systems, CentOS, Alpine, and then somebody requested OpenSUSE, so that's out there as well as examples on how to include root if you want to. If you want to use Docker, I wouldn't do it this way. I would use one of our Docker images. This is built on top of the newly released root Docker image. Even if you don't use that, feel free. You can go and visit the page there. I think you'll learn something about how Docker works just from the root Docker page. And then if you're using NVIDIA Docker, you can use the GooFit CUDA Docker image. So there are a variety of new design features as well. There have been lots of cleanups to the code. It now uses C++11 in many places. This makes it require CUDA 7 or better. There's been extensive code cleanup. Some of it's been automated. There are nice warnings. If you happen to miss an optimization that your computer has, it will tell you, hey, you have AVX 512 and you didn't build for it. Why don't you include that? You can do simultaneous fit to different data sets. That's something that's new. It now supports MPI. You can run on multiple GPUs or multiple nodes, and has some extra optimizations. There are also a couple of new libraries that come along with it. The CLI11 library is, I claim it's probably the most powerful command line parser, but of course I'm biased. I think it is quite powerful. It has infinitely subcommands. It generates its own help documentation. It has 100% test coverage, and it compiles itself into a single header-only file you can just drop into your own project if you want to use just that. And it's designed to support GooFit customization, such as the GooFit toolkit. So it can customize itself and flavor itself to look like GooFit, because it becomes part of it. There's also a brand new copy of the MenuE2 library that was extracted from the sources. There's absolutely no change to the code, but it has a fresh new CMake build system. And again, there's no changes to the code. The official library, which is 5-point-something, that you can download, actually has one change to the code. This one has none. It's fixable just by changing the build system. At some point, I would like to try to get that made official as a replacement, because it's been asked for a while, but I wasn't sure it worked initially. I think it's very close to being ready. So there have also been some new physics features added. There's support for 3-body time dependent amplitude analyses. So, for example, the 0 to pi 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 0 analysis that you saw previously, the k short pi pi analyses have used this. There is also support for 4-body, time integrated and dependent amplitude analyses. And that's something you can look at this CHEP proceedings here for the K3 pi. And then also toy Monte Carlo generation was added using the MC Booster library. That was, for example, used in this CHEP proceeding for model independent partial wave analysis. There's still some more code here that's being merged in later versions, but the Monte Carlo generation is already there. Now, everything I've been telling you is available in the current version 2.0 that was released a couple of months ago. There also is a new version that's being worked on. 2.1 has not been released yet, but it includes full Python binding. That's what we're currently working on. There was a prototype of the Python bindings available in 2.0. This is built by default, but you can tell it to build. And it only had one PDF, an exponential PDF. So it was really just intended as a proof of principle. But now I have a student working on it, Hamadre Pende, and she's added all the PDFs now. We've added a new pip build system. So however you use Python, you can just go here, type these 2 lines in, sol scikit build and CMake, from which are both made by the people who make CMake. And then just pip install. I really recommend verbose, or otherwise you'll sit there and wonder what in the world's happening. GooFit, and that'll download and install, build and install all of GooFit. Same CMake build system, you get all the features I've already pointed out. If you have CUDA, it'll find CUDA and it'll build for CUDA. You'll have a CUDA-powered GooFit. So that's still ongoing. If you do the pip install, you'll actually get the 2.1 dev. 2.1 dev 2, I believe, is the current version out there. I'm assuming that nobody was really that interested in fitting exponentials over and over again, so it makes more sense to have the development version available there. So feel free to give that a try. It may not work perfectly, but if it doesn't, let us know in an issue. Or even better yet, a pull request. So this is an example of what the Python code looks like. This runs. If you just do those lines I showed you, copy and paste this in. Not sure how well that would work from a PDF. And run it, then you'll actually get something. The only thing I'm not including here is the code to make the actual plot. So you do from import star, etc. Then you create your variable. You create your unbin data set. You can create a data set in NumPy and then read that directly in. You don't have to do anything particularly fancy here. You can read directly in from NumPy arrays or anything that provides a buffer interface. Then you create your variables. You put them together just like you would in C++. You then do a fit to. This is a helper that's added so that you can easily evaluate the line of the PDF. And then you get something like this. This is the red line that you get from the X and Y values here. And then that's the histogram plotted normal matplotlib. Not using Buka, though I guess I could. So in the future, a few of the plans that are in some various stage of completion for GooFit 2.2. There's a new PDF indexing system that's being designed by Bradley Hiddle of the Ohio Supercomputer Center. This would allow for much simpler PDF authoring and allow us to go in and make changes behind the scenes later to try to optimize memory layout and things like that. So when this was added, we may not see a huge performance improvement. Might see a little bit, but we might be able to make some larger changes later. We're also looking at putting in the Hydra library. Right now, we have MC Booster, which was the sort of precursor to Hydra. And currently, we're working on making that an optional inclusion, because Hydra requires CUDA 8, which is a little bit of a higher requirement than we have right now for GooFit. There's a GooFit tutorial under construction, and feel free to go there. There's a little bit there that's useful. It's not finished yet, though. And if you're not using CMake 3.8, or better, please start using CMake 3.8. It supports CUDA as a first-class language, and CMake's one line to install. So, in summary, GooFit 2.0 is available now. It's much easier to use than it ever has been before. build system should just stay out of the way. You should be able to just start playing around with it. Lots of great examples and documentation on how to get started on the web page. There's more examples here than before. There's some new PDFs. You even have extra data sets to look at. And you can use things like MPI. 2.1 is coming soon, and adding Python, and then more work is in the Python. I'd like to thank all of the people that made this possible, few of whom are in the room, and support that we received to develop this. Feel free to go to the web page to find more. And if you are out on GitHub, feel free to stop by some of our projects, try them out, give them a star. Thank you.
For the MPI support, does it meet the high performance network, or does it also make sense with the standard cluster with regular nodes and the standard network?
It doesn't really need too high of a performance. I've mostly been using it on one computer, just using that's the best way to use multiple graphics cards. I think Bradley Hiddle has played around a little bit with using it on several nodes. And that would have been set up with a high performance network. That would have been on a high supercomputing resources. So I'm not sure. I don't think it's transferring a great deal of information.
So a question in the comment, comment first, which is those performance plots and show very CPU probably $10,000. It would be interesting to maybe $1,000 GPU. So I know $5,000. Do again.
The one that's shown there, that's 48 cores, it's about $5,000 CPU.
Okay. Yeah, I mean, I always get grumpy on GPU plots because it does not show dollar to dollar.
There are a variety of different things here. Like this is this is the cheapest brand new GPU that you can get, and this is, of course, that's a really cheap. But this is a higher end server system, 24 core. So there's a variety here. This is the MPI running on 2 K40s. So there's a variety of different systems here. It's not perfect. It'd be nice if I had the original RooFit code and I could rerun this on an exactly matching system. But of course, that's not going to really be able to take advantage of the extra cores and things. So.
But yeah, a lot of times normalizing these to dollars can help guide.
So Brian, take a look. So you can see the single core performance on the modern machine. See how it scales to get the number of physical cores to 24. Then you can see how it doesn't scale quite well going from the number of virtual cores to 48. You can compare that number, which is 44 seconds, with the GPU time. And that comes very close to what you were asking for.
Yeah, that's a lot more helpful than I think. So that's just my comment. That normalized by dollar, it's helpful to migrate.
Did you also have a question too?
Just one comment more about dollar. You have also to consider the bill for energy. Yeah. A lot of energy bill.
Well, over zero. So.
Oh, yeah. Otherwise, yeah. He has it at home.
Yeah.
Hey, electric.
Exactly. I have 3 at home. I can afford that. You can afford upside. My CPU is a good number.
The question, now that it's early college, I noticed that for the pip install, you install from source, not binary.
Yep.
Is there a reason? Is that the preferred route, or do you just not know how to get the binaries?
The biggest problem with the binaries is that you really want an optimized version on your machine, and you can't supply. I'm not sure if it has the ability to do this, the different binaries. That's not necessary. This may not always be true. We might eventually be able to supply binaries. No, that was sort of the main reason.
Finding binaries is a hard tangent, and I figured out this once, so I'm happy to share.
Okay. We can definitely talk about that. I haven't really played around with doing the binaries. The first goal was to get this done. I might be able to, if you could, then I think you could skip this first step. This is needed because it's really rough column theming. And then you would just be able to run this and would probably be able to avoid the -d. Actually, there is one other reason why this is probably not a good idea. If you want to add a PDF, you need to compile it yourself.
I was just going to have a comment on that comment, which is if you have a largely C++ project that needs to be compiled, and it also has a Python interface, a more natural distribution system that I would ponder for that's the reason these are.
Yes, but it's really intended. I think this is probably always going to be a build, just because you'll probably go in and add PDFs. You're probably not going to be happy with just the setting that we did.
You might find that your users would prefer to install on this stuff.
You can use this with. You can. I usually use Anaconda, and I'm in an environment. This works just fine inside that environment.
Or fine grained with Zip, you only get to choose master distance.
If you're uploading binaries, I'm not uploading binaries.
Yeah, right.
So I think this is really intended to be a source install. The idea is that you would be able to figure out where this is, you'll edit it, add PDFs, things like that. And you can also, you don't have to use pip, you can also use the original CMake build and add that.
Can I ask one question? So not a build question, but in terms of the Python bindings and as it starts to flesh out, I mean, there's very different considerations going into the core, code design that go into more the user interface side, or how then it connects to the plotting libraries, and certainly it's also a place where the kind of dependency nightmares get introduced and things like that. Can you just say a little bit about how you're soliciting feedback from the community about the different designs? Is it just following a RootFit-like syntax, look very RootFit-like, or there are also other types of fitting packages that are used in industry and in data science that have very different philosophies about how these things are separated?
General design is based on RootFit to sort of look RootFit-like, but if we need to do something differently because of performance, we're fine doing that. It's still supposed to be very usable, and most of the feedback is through things like GitHub issues or just talking to people.
Do you have a process of kind of feedback to the API design? Sometimes in open source projects they'll put out a period where there's a kind of open comments and things like that before people decide.
That's sort of the idea of say, for example, the dev version being available here. This is something people can actually go play with right now.
Right.
And then.
But I mean, less at the level of code, more at the level of API design, a document about where the community kind of feeds back on. For instance, if you look at how scikit-learn was developed, they have a lot of discussion about the API before they implement it.
That would be useful to have. We have meetings once every couple of weeks where we talk about it, and then we talk to a few people using it. But if anyone would like to have more input on that, feel free to send a message, email me, or post something on the GitHub issues.
Okay. All right, great.